Hey there, Akeem Austin here. With Engageable Designs, Family Math at Home. I want to play around with you for a little bit here in this video about permutations and combinations or combinatorics. And for you teachers out there, this is basically coming to you from the probability and data domain or strand, probability and data. And the focus is problem solving, okay? So I have a few things that I will just kind of model first as tools. These are M&Ms. I've had them for a long time. I don't really eat them. They're just here as a manipulative, right? And let's suppose I want to take, let's say I'll take a brown, I'll take a green, I'll take an orange, and I'll take a red. And I got a yellow here, right? And let's say I want to find out how many different ways I can put them in first place. Okay, well, it could be like this. That's first place. It could be like this. That's first place. It could be like that. It's first place. And I forget where I started. I think it was like that, right? So, but what if the race ended differently? If we're racing, maybe the race ends like this. You're in first place, well, maybe it could end like that. Brown's in first place, orange is second, red's third, yellow's fourth, and green's fifth. So I'm showing the different ways or the different orders that this could happen, okay? And just using M&Ms. But here's another activity I sometimes do too. What if I have some vanilla ice cream? I got some black licorice ice cream, if there's such a thing. I wouldn't eat it. It doesn't even sound good, but it could happen. This could be chocolate. This could be mint chocolate chip. This could be strawberry. Who knows? And let's say we're going to take these flavors, and there's 5 flavors, and want to find out how many different ways we can arrange 3 at a time. So the symbolism would be this. Given 5 things, taken 3 at a time, how many combinations could you make? Oh, and by the way, this gets into something called, if you Google this on your own, you can look this up, factorial numbers. And factorial numbers are represented by n factorial. That's not an exclamation point. But anyway, let's come over to our ice cream situation. So I have these 5 flavors taken 3 at a time. So I got my, I'll just go here, vanilla, I got my black licorice, I got my chocolate, I got my, I'll just call it green, right? Mint chocolate chip supposed to be, and then my strawberry. So given 1, 2, 3, 4, 5 flavors, how many scoops, these could be my scoops by the way too, I'm just thinking of it because they're round, could we make? How many different cones could we make? And essentially the idea is that supposed to be a cone here. This, if I change the order, is actually the same cone. That's a permutation, right? So that's the same thing. This would be the same thing, right? And I'm not going to do any cones that look like this where I would have maybe, you know, 2 of those, because I won't do that. So to me, 3 scoops I can carry safely. I mean, it's no fun just to have like 1 scoop, because that's, you can run with 1 scoop in a cone. Anybody can do that. You can run safely, I think, with 2 scoops. But I think it gets really dangerous or tricky to run down the street really fast at top speed with 3 scoops. So let's say, you know, we'll try it, but we would never want to be anything greater than 3 because it might be unsafe. That's just my thinking. Okay, so given 5 flavors taken 3 at a time, how many possible cones can we make? So let's say I'll make V, B, S. I could make B, V, ooh, I can't use S, V, B, B, V, the order doesn't matter. I could use G, right? So, and I'm not going to finish this, but you're just trying to find out, given 5 flavors taken 3 at a time, how many different unique possible combinations that you can make. If someone comes and says, hey, you can do S, B, V, you would say, out. Right? If you're making a game of it, because we've had that combination. And they'll say, hey, we didn't. But we'll say the order doesn't matter because when you look at it, it's all the same. So, you know, you can't do that, right? Combinations, combinatorics. Here's what I really want to show you just now, though. Move that out of the way. Here is a lock called a combination lock. And you can use the same idea of combinations to open this lock. And there are many ways to, actually this isn't a combination lock. I think this is a permutation lock. We call it a combination lock because there's many different possible combinations, but there's only one that will be the permutation that will open the lock. So let's take a look at this lock real carefully here. It looks like the biggest number this lock could dial would be 39. So 39 is the biggest number that this lock can dial. Just notch before 0 on the left. So let's say I get a combination lock and someone tells me that to open this lock, actually I had it written down in the back, I couldn't have worn them out, but let's say this lock is opened by 38, 25, and 3. 38, 25, and 3 will open up this lock. But what if I were given the numbers to someone, so let's say this is the combination, but here's a little thing you can do with your kids at home. Go to this hardware store, get a combination lock for a few bucks from a hardware store, and you give them the numbers like this. You say, hey, you got to use a 3, you got to use a 3, you got to use an 8, a 5, and a 2, and a 0, okay? And there are these 6 digits, and you write them like that, but they're not going to be able to open the lock because that's not the combination. So what if they actually say, okay, well, let me just see if I can sort this out. What if I go 33, 85, 20? Well, we know that won't work because it doesn't fit the conditions of the problem you were given. Conditions meaning the biggest number the lock can dial is 39. So, oh wait, that's not even possible. Great. Well, let me take maybe 38 and put the 3 and the 8 together, and maybe I'll do the 3 and the 5 together, and maybe I'll go 20. Hey, maybe that's the combination. But if you're like me, you're really not that lucky. Hey, wait, oh, by the way, I'm basically also explaining to you how to calculate the odds of winning the lottery. Let me come back to this sheet. Our state lotto game is given by this combination, 49, pick 6. And you're not going to be good enough to get that in most cases. But in any case, so I'm like, okay, well, I just came up with this permutation, but what if it's not the right combination? So I tried it, doesn't work. Well, maybe I shouldn't give up on it. Maybe it's actually 38, 35, actually, sorry, 2, 35. Well, that doesn't work. Well, actually, maybe it's 35, 20, 38. That didn't work. See, I dialed it and opened up. Well, actually, maybe I shouldn't give up on that with those digits, where there's numerals there. Maybe I should go with 35, 38, 20. I'm trying to find every possible combination, and only one of them will be the correct permutation that will open the lock. If I do this for each of these numerals and change the order and find every possible arrangement, one of them will be the combination or the permutation that will open the lock. And so playing around with that is really interesting because patterns will be revealed. Let me mess around with it a little bit further. Let's say 38 didn't work in first place. Well, then I'll put 38 in, first place this way. Then I'll change 38. Oh, wait. 38's in last place. 38's, have I found 38 to be in every place with each permutation? Let me see if I can find any more. I think I can. So now let me try putting 20 in first place. Hopefully I'm not missing anything. Maybe it's 20, 35, 38. I dial it, doesn't work, but maybe I shouldn't give up on those numerals yet. Maybe it's actually 20, 38, 35. If you and I do this enough, we will find a pattern, and we'll know that for every number that's in first place, we'll know about how many sequences that we should find to open up the lock, okay? This is really interesting to me because it's something that is problem solving, but it doesn't require a lot of arithmetical calculations. But as you can see, the problem solving strategy that I'm using is called making an organized list. And as teachers and as parents at home, we know that when we create a list, and if it's organized, it's really well sequenced, then we can kind of see what things should be and how they should fall. So going at this in a random way really doesn't help. And so sticking with a certain sequence of numbers here and then just permutating each one of them until you found each arrangement of those three, dialing those, and then, okay, if they don't work, come up with another arrangement. But I wonder how many possible combinations there are to open this lock. And so go by the hardware store, pick one up, and give it a try. This is called, or I call this affectionately, the ice cream game. What if you're with the family one night and you guys are messing around, you have all these different ice cream scoops, you got a bunch of flavors, and you want to find out how many different arrangements that you can make. Maybe you have 7 flavors and you take 4 at a time, or maybe you have 6 flavors and you take 2 at a time. I don't know. And just mess around with it. And having a manipulative or a device you can move to change positions is really helpful. Play around with it. I'll do some more videos about these that actually shows how to solve these. You can solve these problems with an Excel spreadsheet. You can do these formulaics with a formula and write it out. A lot of different ways you can approach it, but the coolest thing is that you can solve this just by writing down all of the possible steps in permutations and combinations. So hope you like it. Make an organized list, give it a shot.